All right, so on Wednesday we talked about getting signals across the wire, and that we could use amplitude, we could use frequency, and we could use inversion to get those signals across, right? And the most simple case is varying the voltage to send a signal, which is really, we could think of that as something very simple, right? But there's problems with varying the voltage, right? Because you can only turn voltage on and off as fast at a certain speed, and there is a time for it to rise and a time for it to fall. And so we need to come up with more complicated things to get more information across the wire. Now, the other thing that we talked about is if we do the simple voltage scheme where highs are ones, right, lows are zeros, so this becomes 1, 0, 1, 0, 1, is we could have different levels of voltage, right, where we could represent something else. Now, if we want to represent something else, that becomes the symbols. That becomes representation of symbols. So right here we have a very simple modulation scheme, 1 and 0, correct? What if we wanted, and this represents 1 bit per signal, right? What if we wanted to represent 2 bits? What do we have to do?
4 levels of voltage.
We have to do 4 levels of voltage. Why 4 and not 2?
Because each bit in the pair has 2 possible states.
Correct, correct. So we would need 4 levels. So the base, right? And this would be 0, 1. This would be 1, 0. And this would be 1, 1. Right? Hold on just a second. And if we wanted to represent three, what would we need? 8, right? So however many bits that we want to represent, right, 3, right, it is actually 2 to the 3rd that we need to, levels that we need to do. So we also talked about the problem with too many zeros being in a row. I mentioned that, hey, what if we have a number of zeros in a row, because it's very difficult for the machine to read, right? Because we don't have super accurate clocks. And so we need to be able to get rid of those numbers of zeros. And what we can do is we can set up a table where 5 bits represent 4 bits. And you can imagine this table where we can say, hey, the rule for the table is that you will have no more than 3 ones in a row. Or 3 zeros in a row. So you could have the bit 0, 0, 0, or 0, 0, 0, 1 mapped to some other table where you can't have 3 zeros in a row, so it could become 0, 1, 0, 0, 1. Right? We could do a mapping clearly of all of those. Now, that would get rid of all of the zeros so that we have less possibility of having zeros in a row. But the problem is that we can still have a number of ones, which is really the same problem. Right? If we have a number of ones in a row, then we still have the same problem. So we need to come up with a different scheme to get rid of the ones. So in our very simple scheme, right, this is a simple scheme called NRZ, non-return to 0, right, where 0 is the low and 1 is the high. And so we could come up with a different scheme and say we could say basically the same scheme, non-return to 0, but on a 1, we will invert. So we have a mapping. And let's say we want to send across, let's do this mapping. So 4 zeros becomes 1, 1, 1, 1, 0. 1 becomes 0, 1, 0, 0, 1. Then E becomes 1, 1, 1, 0, 0. And F becomes 1, 1, 1, 0, 1. So this is an actual mapping. If you look in your book, the full table's there. But now we have 4 letters. We have 0, 1, E, and F that we can send across the wire. So let's send that across with NRZ. Right, so put tip marks down here. This is our timing. So we're gonna send 0 first, and then we're gonna send 1 second, E third, F 4. Right? So 0 would become 1, 1, 1, 4 ones and a 0, right? So our mapping looks like 4 ones and a 0. And then we're going to send 1, which is 0, 1, 0, 0, 1. So 0, 1, 0, 0, 1. And we're going to send E, which is 3 ones and 2 zeros. So 2 zeros. And then we're going to send F, which is 3 ones, 0, 1. I missed 1 tick. So this would be NRZ. The problem is that now we have large strings of 1s. In this case, we want to get rid of this. So we're going to do a different scheme on top of our mapping. So we're still doing a 5-bit to 4-bit mapping, right? Which is losing bandwidth, by the way, right? We're using bandwidth to send extra bits across. But now we want to get rid of this large string of 1s. So what we do is we will invert. So I'm going to set our tick marks in the middle of the other tick marks because it becomes easier to recognize what's happening. So on 1, we invert. On 0, we do nothing. So we come across on 1, we hit a 1, so we invert. The next one is a 1, so we invert again. The next one is a 1, so we invert again. The next one's a 1, so we invert again. The next one's a 1. Oh, I'm reading these things, sorry. So there's an invert in here. And then this one is a 0 for 2 counts, right? So we do nothing for 2 counts. Then we have a 1, so we invert. And then we have a 0 for 2 more counts. And then we have 1, 1, so we invert, 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 invert. And I think technically that's it. And then a 0 for 2 counts again. And then we invert on 1s. 0 for 2 counts, invert on 1, and then we're out. Now, it's not like you're going to have this on a test, right? But notice that now, with these two schemes, it is not possible to have long strings of any number. Is there any other benefit that we've got out of this?
The signal will be enhanced.
The signal is enhanced how?
The input will be higher. So we don't want to lose it easily.
So we've actually inadvertently added some information to our signal. So our signal looks much more like a random number, right? Randomly generated. Which means that we have frequent inversions. If we have frequent inversions, we can now average out the inversions, right? And we can now get a clock. It is impossible to have long strings of zeros. It is impossible to have long strings of ones. So now we can actually derive a clock out of our signal. So we've solved two problems, right? One is we didn't have an accurate clock, so we needed to get rid of long strings of ones and long strings of zeros. It becomes difficult to read, right? But instead of just adding a clock, so we could add a clock. We talked about this last week, right? That, you know, we just add a really high signal for the clock. But we don't no longer need to do that because our pattern is actually allowing us to derive a clock itself. We can derive the clock right out of it. And then when we add framing to it, we can get guarantees of clocks. So this is NRZI, but the entire coding scheme, not that it's super important, is called 4B5B. We map 4 bits to 5 bits, and then we use inversion on ones to keep this large strings of ones out of the way. So now we can send a reliable bit stream across a wire, at least-ish.
And this is what they do today?
Well, so this is a simple one. It's actually most of the ones today are like Manchester, but it's the same idea. It's more complicated because this is wasteful because we used we lose an entire signal pass for every 4 bits we send across so there's more efficient ways to do it. But this is the idea, right? The base level idea is like, hey, let's get a clock and let's get rid of long strings of zeros. Now we could come up with more complicated schemes to maybe only lose a 30th rather than a 5th of our bandwidth, right? So there are more complicated ones. Manchester encoding is very popular, but it all comes down to design. So let's talk about limits. So we're trying to send this. If I can have as many signals as I want, what's my bandwidth? If I can put in these symbols, right, and put as many as I want, what's my bandwidth? It's infinite, right? So there might be some limits that we have to deal with. So what are things that are influencing our bandwidth? Attenuation. What else?
Signal loss.
Signal loss. That's kind of attenuation. What's the big problem with attenuation? Huh? Well, attenuation always grows with distance. So you have signal degrades over distance. But what's the problem? We talked about this, right? So we have a wire, right? And we start out with a signal and it attenuates as we get further and further down. Why is this a problem? If we had a clean signal, this wouldn't be so much of a problem, right? The problem is noise. Noise on the wire, or more importantly sometimes is noise on the sensor on the end. So you have a sensor down here and it has thermal noise. Like when there is no wire connected to it, it receives a signal. Just because of things around it. Right, so there are thermal noise in here. And so just think of this noise as some kind of random signal. The problem is that once the attenuation gets too small, you can no longer determine signal from noise. Right, so noise is the big issue. And on our very, very simple scheme here, where really this is a wave, it's not binary. On our very simple scheme here, how much information can we pass with no differentiation in symbols? Let's just forget symbols for a moment and say there's only one symbol up and down. How much information can we pass? Maximum. So I can send a 1 here, right? And I can send a 0 here. I can send a 1 here, I can send a 0 here. So if I had a never-ending strings of 0s and 1s, right, this wave would be entirely maxed out with information. It could not hold any more information. So a full wave from crest to crest, right, can hold 2 symbols. Two symbols from crest to crest. Now this is a maximum, doesn't mean that we will ever get there, but we're trying to, it would be useful for us to think, hey, what is the theoretical maximum bandwidth for this particular medium? Right, and then everything else becomes engineering decisions to try to get as close to that theoretical maximum as possible. So if we can send 2 signals per wave, then if we had a noiseless system, right, where we can send as many symbols as we want, we're not going to influence noise, then if we pick an arbitrary number of symbols, what is the maximum number of bits? The formula. Think about it in your head. Right? Where B is bits. It's to the B to bits, right? So if the inversion of power of is what? So if we have or let's just use this as S for right now. So the number of symbols, right? The log, if we take the log 2 of the number of symbols, that would be the amount of information we can send across that. Right? And of course, it's not just 2. So this is a measure, if we're measuring a wave, a periodic wave, what is that? Huh? It is frequency. It's measured in hertz, but in electrical engineering, what is hertz? Is a measure of what? Not computer science, but electrical engineering. Hertz is bandwidth. Because obviously, if we have this wave, right, we can send more information than this wave. Correct? So we come up with a formula, 2 times the bandwidth, then log 2 of the number of symbols. This is usually represented as B. But it's 2 times the bandwidth, the second log of the number of symbols. Right, that is the amount of information we can send across a wire in a noiseless system. Now let's talk about noise. So let's imagine we had a number of symbols. These are our different waves, or different symbol levels that we put across our wave, right? So again, 0, 1, 2, 3, 4. In the sense of having more than 4 right now. Right, the next one we'd have to have 8, right? The next one we'd have to have 16 to be able to differentiate any other bits. Right, and we can build some kind of wave across this with our modulation that we talked about last week. So imagine we have this, but we introduce noise. So let's say that the noise is somewhat slightly smaller than one of these levels. So if the noise is somewhat slightly smaller than one of these levels, so let's move this up here. That means if I have a signal that lands anywhere in here, I can differentiate the level. Now, we've been representing the symbols as a larger wave, like amplitude or something, right? But in reality, right, our bandwidth is this. So if we want to go to 8 symbols, we don't make it any higher. What do? What would we have to do? We can't make it any higher. This is the maximum bandwidth right here. And this is the minimum. If we can't make it any higher and we want more symbols, what do we have to do?
Increase the frequency.
Huh? What we do is we put
All bands.
right? So it becomes 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? We can't increase the bandwidth, right? We have a bandwidth is usually constrained. We say, hey, if you go to the FCC and get a license, it says your bandwidth is from this megahertz to this megahertz, right? Or this gigahertz to this gigahertz. We can't get any further than that. If we could put a lot more information in there, right? So bandwidth is usually constrained, and it's either constrained by a regulation or it's constrained by a physical medium only operates well at this bandwidth. So what we do is, in order to get more symbols, we have to divide the bandwidth into different symbol tables, and we keep dividing it in half to get more and more. Right? Notice in my example, we have a little bit of room right here that we might be able to do something special with. The problem is in order to do this, now our noise ratio needs to be slightly smaller than that. Because if it's not, we can no longer differentiate the symbols. So what we have is we have a signal going across, plus the noise. And then in order to differentiate it, we need to divide by the noise. So in my first example, before I divided this thing in half so many times, right, where we had something really simple as 4 levels, right? And so long as our noise ratio is smaller than this, then we can get the amount of information across, right? It's proportionally correct. And is the signal plus noise over noise is the actual formula to derive how many symbols you can get in a table. So if we take this as our symbols and we stick it in here, then our real bandwidth, theoretical limit in a real system that has noise, becomes and it's 1 plus, because you can divide the in out. That becomes a measure of capacity for a real system. Notice that if noise is 0, right, we're going to have a dividing problem. But as noise approaches 0, our bandwidth becomes infinite, because we're dividing noise out. And this is really because it's n plus s over n, which is 1 plus s over n. And that becomes the actual capacity of your network. That is the theoretical limit where you can never go above that. So you always try to engineer close to that. But it's useful to know how high you can go. Now, noise varies greatly. So while this is a real noise signal to noise ratio, so the actual signal divided by, or 1 plus the signal divided by the actual noise, noise is almost always represented in a logarithmic scale, in decibels. So in order to get real noise in any assignment or any real problem, right? You'll be presented with something like your noise is 30 dB. If your noise is 30 dB, what does that mean? Any guesses?
It's a level of 5.
Huh?
A little shy of 5.
Close. So decibel is actually a log-based 10 scale, but it's also multiplied by 10. So 10 dB noise is from 0 to 10 is 1 to 10, right? It's multiplicative of 10 every time you go dB. So 20 dB would be 100 times, right? 30 dB would be 1,000 times.
And 10 dB is just 10 times?
10 dB would be 10 times. And the actual, it's running out of space to good. It's basically 10 log 10 signal noise ratio. So the real signal noise ratio. So now, if you're given a dB, a signal noise ratio, you can calculate the real signal noise ratio, right, in a non-logarithmic scale. You can plug it into our formula over here, which came from a guy named Shannon, and you can now figure out your information capacity. And that cannot be overcome. That's the maximum amount of information you can send on that wire, or through the air. So let's talk about some real-world practical scenarios. So if you're engineering over a wire, what are some of the engineering considerations? Let's just do this and compare and contrast. If you're engineering a wire versus engineering like wireless.
conductivity of the medium, right?
Yeah.
What is it? Copper, metal? What other type of metal?
It's almost always copper, because copper is relatively cheap compared to other things that conduct electricity, like gold, right? But if you're engineering a network, wireless versus wire, right? We have some different engineering considerations. One, if you're engineering a wired network, you can say our maximum wire length is this. Why would that matter?
Affects delay times, return.
It does affect delay times, and that's going to become very important in the leak layer. What else? It also constrains attenuation. If it constrains attenuation, it constrains our signal to noise ratio. Right? So at the end, the attenuated signal could be measured, right? And we can build wires that are fairly consistent. And so if we can build wires that are consistent, then we can measure that signal at the end, and we know what the noise is of our sensor. So signal to noise becomes constrained. So then some of the other engineering consideration would be, what is the possible bandwidth that you can send over copper, right? That really becomes it. It becomes length, because that is delay, and it becomes the usable bandwidth over copper. Now let's think about that in a wireless situation. Can you constrain attenuation and or noise in a wireless environment? No. Why?
You don't have control over the air.
You're not manufacturing the air, and you're not manufacturing the environment the air is in. Right? And we have other attenuation problems. We have reflection issues, right, that we talked about last week, right? That a third of a meter can mean or sixth of a meter is what we calculated out last week, can mean the difference between no signal and double signal. So in wired system, typically you pick your medium, you pick your delay, and the medium has a measured bandwidth, whether that be like Cat 6 or Cat 5 or whatever else. It's the manufacturing process for the wire produces this amount of bandwidth. Or fiber is the same thing, right? That you can stick this much light in these bandwidths, because glass, by the way, is opaque to some light, right? So some light travels through glass great, and some light doesn't travel through glass at all, and there's obviously some that only do mediocre, right? But we can measure that as we send light through glass, and we can say, hey, this glass is really good for this bandwidth of light. So bandwidth now becomes an engineering decision based on your medium, just like wire. There's no real difference. The only difference is wire tends to be baseband, 0 to something, and light tends to be passband, which is somewhere in the middle. You have a carrier signal and you stick stuff in the middle. But wireless becomes a completely different animal. So in wired and fiber networks, you tend to have a known signal to noise ratio, and you engineering around that. And that way you get a very defined computer science bandwidth. Your bandwidth remains static. 1 gigabit Ethernet is really 1 gigabit. It's not sometimes a half a gigabit, right? It's really 1 gigabit. Now, does that mean that you're getting a gigabit of information out of it? Maybe, maybe not, depending on how you define things, right? But it is static. So 54 megabit Wi-Fi is not 54 megabit, not most of the time, because of all of the noise, right? So, and it really becomes is if your noise grows, you now need to reduce your symbol table. And you need to have a mechanism that you engineer into that to say, hey, we're instead of having 8 symbols, we're now going to have 4. And then when 4 doesn't work, you're going to have 2. Right? So as we go through, let's think about that. Now let's talk about a somewhat real world example of how all this comes together. What is DSL?
Using the old phone.
Huh? It uses the old phone
Four
line.
wire, I think.
Huh?
4 wire.
It's 4 wire. That's right. I believe it's Cat 3. It's definitely 4 wire though. Now, interestingly, in this, we have a little bit of both problems. It's a little bit like wireless, and it's a little bit like a wired network. Why? So, and the reason is because we're using existing wire.
Because there's no limit on how long.
There's no limit on how long. So if you were designing Ethernet, you say 100 meters. Right? And then that's it. Like 101 meters doesn't work. So, but this is now we're using an existing wire, right? So there's no real limit to how long it can be unless the signal noise ratio becomes bad. So if we have house over here, and then the switching station, the building. So DSL, the problem with it's a wire network and it should be a wire consideration, but we're using existing wires. And because we're using existing wires, of varying quality by the way, but the main thing becomes the length of those wires. We can't constrain the length because the houses are just different distances from each other. Now we still need to have voice. So voice, if you read in your textbook, can be completely represented in 4 kilohertz. Everything that the human ear can hear can be represented in 4 kilohertz. And that's analog. But this wire has a usable bandwidth of 2 megahertz. And above 2 megahertz, the wire itself is no longer reliable. So the wire you have a band-based engineering, electrical engineering bandwidth of 2 megahertz. But it only uses 2 kilohertz. So what can we do? Let's design DSL. What are some of our engineering considerations? What is DSL normally used for? How are we going to sell this?
Modem.
Huh?
Modem.
It's not modem. Right? Modem was using analog sound to transmit information. Right? It's something different, right? We're going to actually use manufactured wavelengths to go across this wire. Above 4 kilohertz, but smaller than 2 megahertz. But what's the main use for DSL? What do we use it for today? Internet. So when somebody gets on the internet, from a network perspective, what are they normally doing? They do connect. You connect, right? Let's just think. You go pick a website. I don't know, Facebook. That's what everybody uses, right? So you connect to Facebook, right? So now we have this two-way communication between Facebook and me. Is that two-way communication equal? No, it is not. What is most of it?
Most of it's going to be download.
Most of it's going to be download, right? Much bigger than upload. Notice that you have to have upload because you at least have to be able to connect to Facebook and tell them to download stuff, right? So, but download is going to be much greater than upload, though that's actually changing today, right? Because we push videos and pictures and stuff up to the internet all the time. It's actually becoming closer to equal, but in general, you still download more than you upload. Now, we have this big bandwidth up to 2 megahertz up here. How are we going to allocate this? Who's had a DSL line ever? Anybody actually had a DSL line? Do you remember like what the bandwidth schemes were?
Like how much bandwidth I got?
Yeah.
It was like 12 megabits.
So it's like 12 megabit download, right?
And like 1 or 2.
And then like 1 or 2 upload, right? Let's just call it 2. So you have 12 megabit download and 2 megabit download. But some guy that was closer over here, if this was you, right? Some guy that was closer might get 424. And it would be an even multiple of that, right? If you looked at the DSL schemes, normally when you went to DSL, you would say, hey, I'm interested in DSL, and they would evaluate, you'd fill out your address, and it would say what your available bandwidth was. And when you filled out your address, what they were really doing, because they know what wire's in the ground, because they're the phone company, they know that there's this much wire between the switching station and your house, and they could just calculate how many symbols that they could put on that wire. Now, from a bandwidth scheme, right, this is the 12 and 24 and the 2 and 4, that's a computer science type bandwidth, right? But what we're really talking about is electrical engineering bandwidth here, right? Which is 0 to 4 kilohertz, which is unusable because we're going to use that for voice. And then 4 kilohertz to 2 megahertz, what we're going to use for data. And we're also going to leave, for engineering considerations, we're going to leave a little bit of space in there. We're going to put a filter on your phone line. If you remember DSL, you actually got filters, right? And the filter would allow your phone to pick up only up to 4 kilohertz. It was actually a little higher. And that way all of this high bandwidth stuff that was going over here wouldn't affect your voice conversations. Right? Because waves combine. So even if you had high stuff going over here, right, waves combine, so it could actually affect what this sounds like down there. So, and then this was completely analog, and this is digital over here. And then, if you couldn't fit enough symbols, if you could fit the maximum symbols, you went in and said, hey, the noise for this particular line is, some arbitrary number per feet. You can figure that out from an engineering decision. And then you can figure out how many symbols you could put in this bandwidth. Guys that were really far away could only get 1. Now, if you had 1 symbol, going back to our equation here, right? If you only have can only fit 1 symbol in here, right? You still get 2 bandwidth times the bandwidth to be able to send that in. right? Which is just short of 2 megahertz. So you would have just short of 2 megahertz of actual bandwidth that you could stick from a theoretical limit. Because you can only get one symbol in there. If you get more, then your DSL would go up, because you got 24 rather than 6. So, the problem with all of this is if noise was static, right? If when we say calculate the signal to noise ratio, if noise was a fixed value, then we could send stuff across a network without error. But is noise fixed? So when we say signal to noise ratio, what does noise here actually mean? That's an average. This is our average noise. Doesn't mean that there can't be spikes, right? But we measure noise in some kind of average. It's actually a skewed average, right? Because you wouldn't want to use the actual average, because then half of your bits would be errored out if you were approaching that limit, right? But we do a skewed average, but there can be spikes. So let's say that noise for, just to make everything easy, let's just say that noise was skewed by 90%. So 9 out of 10 times that noise ratio is correct, right? But on the 10th time, in some kind of random fashion, you'll get an error. But since noise is average skewed, it doesn't matter how far you skew it, right? If you do 1 in a million, you're still going to get an error on average every millionth bit. So we need to be able to build error correcting or error detection into our networks. How do we, what do you guys think you would do to build error detection or error correction? Let's just start with detection. How do you do detection?
Measure it over time.
But we're sending data now. So we're sending a stream of bits.
Checksums.
Huh?
Checksums.
So we could send a checksum, right? What's a checksum?
It's a hash of the data that we sent.
Yep. So it's some kind of message digest. Not normally cryptographic message digest. It can be reversed, but it's some kind of number that allows us to check a larger number against a smaller number. But even simpler than that, how would you do it more simple?
Acknowledgements.
Huh?
Acknowledgements.
Yeah, but that's getting up into the transport layer. We just want to. Some networks are one way, right? So how do we do that?